Demystifying Machine Learning, Creating an Art-Making Twitter Bot with Machine Learning, with Nick Walsh.
So thank you again for having me. So today we're going to be talking a little bit about how you can build apps with machine learning. Paige did a really great job of going into specific details and different algorithms and implementations. And so I think more from like an architectural point of view, how that fits into your apps is something that's very intimidating for a lot of people. So I wanted to talk a little bit about that today and show you a really cool use case that I had where I built a Twitter bot that uses AI to stylize your images. So a little bit about myself first. Hi, I'm Nick Walsh. I am a developer evangelist at Datmo. We help to build machine learning and AI tools for developers as well as for enterprises to help deploy and manage those things. And I also really like helping at Major League Hacking, where I help support student hackathons all over North America. So just live and breathe code, hackathons, and building cool things. So a quick roadmap for today's talk. First, I'm going to go into what is AI and ML. Again, I won't harp on a lot of these things because Paige did a great job with that already in her talk. But then I'll quickly get into what that looks like more so from the architecture perspective, examples of how you can use that in your apps and how it's a little bit more familiar than you may already think. And then lastly, we'll go take a look at the code for the Twitter bot example that I've spun up. So first, what is AI and ML? So this is a very similar image to what you saw in Paige's presentation, but essentially AI is, from a broader perspective, apps with the ability to dynamically respond or behave based on conditions, which a lot of people think at a most basic level can sort of be like if statements or basic conditionals. And actually, you're not too far off with that assumption. Some extremely valuable and powerful AI algorithms like decision trees are actually based on sort of like just nested decisions. But the special sauce is really in how they determine what those conditionals will be. Whereas more specifically, machine learning is the use of algorithms and apps that have the unique ability to improve themselves as a function of giving it more input data. So I know that's a lot of words again, but I think like having it all phrased out multiple ways, one of those ways will click with you. At least that's how I see it. So machine learning algorithms help learn without relying on a predetermined equation as a model. If you can think of machine learning as sort of like an equation where you're giving it a new piece of data and it's going to make a decision based on prior behavior or experiences, you want to train those behaviors and experiences on a set of data. And so the algorithm will dictate how your data is being crunched or processed, but it's not a predetermined sort of equation where you can just download the model and just plug a new piece of data into it immediately. You always need to supply it with some sort of training data. And ultimately for machine learning, the whole idea is that with more data, we can improve these boundaries or this model to adaptively improve the performance over time. Whereas if you just have a bunch of if statements that are hard-coded, that can't necessarily improve itself, right? So the beauty of machine learning algorithms is that if we can alter or augment our data set over time, the resulting output of our model, the accuracy, and a lot of these metrics can actually get better over time. And that's really, really powerful for a lot of reasons. So in short, all machine learning is artificial intelligence, but not all artificial intelligence is machine learning. I think this draws parallel to the whole like all squares are rectangles, but not all rectangles are squares type thing that we learn when we're doing math in middle school or elementary school or whatever. But again, this is kind of semantics. A lot of these phrases are used interchangeably and for good reason. Since all machine learning is artificial intelligence, when people reference them, especially from a mile away, a lot of them, the things that they're talking about are very similar. So what is AI going to really look like in our apps? So there are two very distinct parts, and I think this is really where people get tripped up because it's never one or the other. It's always both, whether you're doing both or you're abstracting one of them away. So two distinct steps. First is the training step where you build the model. And the second step is the prediction step where you are going to invoke that model with a given piece of input data. And so for training, again, that kind of touches on what I mentioned before, where you want to use past behaviors, past classifications of data that you may already have to be able to map some sort of relationship between your data, such that if I have a new piece of data, this model or this system should be able to give me some sort of output of where it thinks it lies based on its given new statistics. And so the model is built in the training step, but then the prediction is done in the second step. And so I think we understand prediction from a architectural perspective, but training usually is where people get tripped up. So the way I like to think about it is that AI at a very broad level can always be conceptualized to behave like a function. AI collectively is very hard to conceptualize that way, but if you break it into the two individual steps as two separate functions, I think it'll start to become a lot clearer. And I'll show you that right here. So the first step is training. So in machine learning, you have a handful of components here for this step. You have the input, which is going to be a hyperparameter configuration, but I'll circle back around so that you can understand that better. The main thing you're probably used to seeing is maybe what that black box is, which is the algorithm you're going to be using. So for example, if I want to use a k-nearest neighbors clustering algorithm to develop clusters of data, I don't necessarily understand them. You may not understand necessarily the math behind how that works under the hood, but the point is that it operates like a function. It has a given set of inputs, which are like a configuration. It also accepts training data to then generate those sort of clusters around, and it's going to return an output, which is a model. And so as anything, if you change the inputs, you're going to get a different output. So for one given algorithm, let's say like a clustering algorithm, right? You can change your hyperparameter configurations and have the same training data and get a different output. Or conversely, you can run the same hyperparameter configuration on many different sets of training data and also get a different output. And Paige also touches on this, where essentially the difficult part of machine learning is that you're no longer just tuning one knob. You have like multiple hyperparameter configurations, countless other properties of your data that you can be tuning, and sort of adjusting all of these sliders when doing training or before you start training is a very difficult sort of problem. But essentially, if you can think of training as input of a configuration and data and an output of a model, then it makes inference and predictions a lot easier to understand, because now you have a new black box. Essentially, once you've done your training, which is typically a very sort of like static operation, it doesn't like continuously happen in real time unless you have a very special use case. You have a new system where you have the model as your black box. You input a new piece of data, and the output is going to be a prediction. And that new black box was formed based on the model that we built in the prior step. So AI, from a broad perspective, very difficult to understand if you try to put those things together at one time. But if we can separate them into the two steps, I think it becomes a lot more clear about how these moving parts sort of fit together. And so when you think about it from the sort of like paradigm of these are really just a sequence of functions or different types of functions, I think that becomes a lot more digestible, because we as programmers already have lots of different ways to deal with these things. We deal with them all the time separate from machine learning. We have our own APIs. If we have a function that does something that's very complicated, for example, like sending emails or sending like SMS, instead of sort of doing that from scratch, we can get an external API that does that. Alternatively, we can build out an internal API if you have a very distributed or large sort of like production pipeline. But even on a simpler level, we do this when we download language-specific packages, right? Like whenever you do pip install for a package in Python, you are essentially using the code and the functions that someone else has already built with some sort of neat and convenient wrapper. And then alternatively, you can even go the open source route where you're directly cloning other people's work. And as long as repos and projects are following good conventions, it should be pretty easy to be able to understand, okay, well, this is the functionality and it accepts this input and this sort of output for this piece of code. And so we're used to that. We really understand how that works. So I think the big challenge is how can we both understand how AI can fit into this sort of paradigm, but also how can we structure our apps in such a way where they fit into this paradigm so that we can not get really stuck on that. So let's talk about that for a second. How can we use AI in our applications? So there are a lot of different use cases and a lot of different forms. And I think this is where people also try to get a bit overwhelmed because they seem so very different. And the theory for optimizing each of these is extremely complex. But at the core level, if you break it down, these all sort of follow some sort of continuous schema where you have, for predictions here, you have a given input on the left. So for example, if you want to detect that there are human faces, let's say that's our model, and it has a binary result. It's either 0 or 1. The model will say either there are no faces or there are faces in the model. And so the input is going to be a picture for our function. The function, the black box, is going to be a model that's already, let's say it's already trained. And then the output is going to be a 0 or a 1, where it's going to say either there are faces in that or not. And this analogy can kind of like go through to all of these, regardless of whether they're a binary classification problem or not, right? So another popular use case is natural language processing, NLP. With an input of an audio clip, we put it into a model that's been trained, let's say, on hundreds or thousands of hours of transcripts with audio files. And the output is going to be some sort of text transcript of the audio clip. And then once you have that output with this function, you can build anything on top of that in the same way you can with regular programming, right? So if you have, for example, let's go back to the human faces example, if there are faces in a given image, you may want to prompt the user to maybe tag those faces, which goes in line with the Facebook example that Paige mentioned earlier. Or as well, you have a loan application example. If they wouldn't repay the loan, then the logic on top of that would be do not offer the loan to begin with. So lots of different things, but the entire idea is that if we can understand the input, understand the output of the model as well, we can use those model outputs in the same way that we really use any other sort of like logicals in our code or conditional sort of like programming. So there's a few tips I'm going to have here, and I think that, like, again, it's very important to sort of like demystify, again, in line with the title of today's talk, kind of how all this happens under the hood, because I think it is very, very difficult to sort of approach the AI and ML world for a lot of developers because of how many, not necessarily buzzwords, but packages and tools that there are available, and it's really easy to sort of be overwhelmed. But I think the flip side of that is that there are a lot of tools to make your life easier should you take the dive and try and take a look at them. So if you're writing your own code to perform ML, or you want to do this training yourself, sort of, I say from scratch, but that's even a relative term, you don't have to reinvent the wheel. There are lots of libraries out there where the researchers that are working at labs all across the country and at big companies, they're optimizing and squeezing out all of the performance that they can out of these algorithms. And so they wrap those in really convenient sorts of frameworks. So when you want to code, you don't want to have to worry about writing assembly code under the hood about how your code and functions and logicals are going to work with your register and like your processor in your computer. You just want to do the high level sort of stuff. And it's the same thing with machine learning a lot of the time. Unless you're really trying to alter the way an algorithm works or individual components of the machine learning pipeline, there are so many different tools and frameworks available across many different languages. So really leverage that, because you'd rather not get frustrated with sort of like the semantics of implementing something that you already know how it should work. You'd rather be able to extract the value or get to the valuable part of machine learning, which is training on your data and getting to those predictions. So there are a lot mentioned here, and they all have very specific, or not very specific, but a lot of them have the sort of things that they're best at. And so do your research, look at your use case, and choose one accordingly to that. Power of AI frameworks, again, is the abstraction. It's sort of like the scoping, how much abstraction you want is very much preference-based. But you can a lot of these are available across multiple languages even for some of these frameworks. So sort of pick what resonates with you best or has the most resources available to help you build the models that you want to build. And then if you have a really common use case, for example, there may be an API or a service that already does that. So let's say, for example, that you want to do something like sentiment analysis, right? Like for either text or for faces in an image. Well, that's a problem that's very well known. There are lots of people working on it. So there are actually APIs and services you can pay for to already do that. And as with any sort of API that you're paying to get access to from a third party, you get a lot of benefits with that. They've ideally optimized a lot of the accuracy on it. You don't have to handle any of the ops of the API, really, because they're doing all of the hosting. And all you need to understand is the interface with that particular API, which in most cases are just RESTful API calls, which, again, we should all sort of be used to from a lot of different things outside of AI and ML. So there are a lot of examples of this. Google Cloud Platform has some APIs for deep learning, Amazon Recognition, Clarify, Azure. These are a lot of like computer vision examples. And so those are definitely worth checking out if you don't really feel compelled or have a reason to deep dive into AI and ML, but still want to access that value. This may be a more reasonable trade-off for you. And so there are pros and cons to using third-party APIs. Pros, they're obviously very simple. We're used to RESTful API calls and how that sort of fits into our architecture, and they're quick to implement. But they are not always perfect in the sense that, let's say you have a very specific use case or a very specific set of data. Some of these models are usually trained on more like general sets. You kind of like trade off accuracy for specificity in a lot of those models. And so if the models don't necessarily fit your use case as ideally as you'd like, your accuracy may go down, and they may not be able to perform at the accuracy that you may need for your particular use case. And although they abstract all the ops away, costs can add up depending on how many calls you have to make to these things. And so if you're looking to deploy AI and ML in production, that's what my company works to solve at Datmo. Essentially, it's a whole beast. There's lots of different problems with that. And we work very hard to try and, again, help your company get through that. But ultimately, it's a very difficult problem. And there's lots of constraints that are different from traditional software. So while I'm a really big proponent of understanding AI in sort of like the functional sort of paradigm, the ops and the architecture that goes behind the scenes, where a lot of these frameworks sort of abstract that away, when you get to deploying that in production, that can be very dicey. And that's actually where APIs may become very valuable to you, depending on your use case. And then on top of this, there's a lot of trade-offs that I think are unique to AI and ML that people don't really think about in traditional programming, or rather, they may not make a huge difference. So an example is training, number of epochs until it scores well. A lot of algorithms have an iterative process whereby you can continue to crunch on your data set, and ideally it will keep performing well. People typically don't grade code bases by how long they take to test and compile. Obviously, there are things that you keep in mind, but in machine learning, these things can kind of balloon exponentially depending on your algorithms, the efficiency, the data set, the data type, et cetera. And these actually become very big factors when it comes to thinking about AI and ML. You may choose a model that's slightly less accurate if it means that it trains 10 times faster, and it's a model that you need trained consistently on new live data, for example. These are trade-offs that are not absolute. They're sort of like preferential, and that's not something that always happens to that extreme of an extent in traditional software engineering. Again, another unique thing with AI and ML, a lot of times in training and even prediction to a lesser extent, you can parallelize these processes with GPUs and make them go orders of magnitude faster. And so depending, again, on your use case, how fast these predictions have to come out. These are like throughput constraints. Or for training, can we cut that down? Can the training time that we reduce offset the server costs of getting GPUs? These are all things to consider. Memory, some models are extremely bloated. Let's say, for example, you have a model that's trained on everything, a general model that's trained on maybe everything you could see if you walk out of your house, and to identify each of those things as a different entity. That could cost a lot of memory to store. And for mobile applications or like an onboard sort of machine learning model, let's say for Apple's Core ML or Snapchat, that can be a very big constraint. And then inference time, how quickly do you really want this to process? That can obviously be a very big thing that you're worried about. So I'm going to talk a little bit about one example that I've built that I think is really exciting. And hopefully it will showcase how easy it is to really plug AI and ML into the existing architectures that I know you know so well. So the example for today, again, the name is Starry Nightbot. I got this after Vincent van Gogh's Starry Night painting. And so essentially what this is going to do is it's going to take an input image, which is that line you see in the top left. I've trained a model on the Starry Night painting in the bottom left to generate a sort of like style mathematically under the hood. And so with a given input image for a lion, it will, or any image, it will output a stylized version of that. Which you can see here on the right-hand side. So let's go over the architecture of this app before we start looking at any code. So as a Twitter bot, obviously, I'm going to be using Twitter's API. And essentially, if you look at our app, it's fairly simple. You kind of only have 2 files that do a lot of the heavy lifting. So for our app, let's first look at Twitter bot. I coded this in Python, and essentially, how this starts out, you initialize the stream when you spin up the, when you initialize the script. We have this connected to Twitter's streaming API. So you're actively listening to for a certain conditional or a certain event. For the Twitter bot, in this case, I want it to be able to respond every time somebody tweets at it. So you can sort of set that. And so while it's listening to the stream, it will then capture valid tweets from the Twitter fire hose using the streaming API. And the response from Twitter is essentially just a RESTful response. You can extract any sort of metadata, the body, images, etc., attachments. So we're going to extract that image from the API, from the API response. Then we're going to throw that over to our AI machine learning sort of black box. And I'm not going to dive too deeply into sort of like how that model is built. I'm going to link it to you so you can see for yourself if you're more interested. But I think it's more valuable to just show you how this fits into the architecture. So once we have the image, we pass it through the function for the style transfer, which is just in this example, going to be a locally running machine learning model with a prediction function that's ready. And that function is going to return the image to our Twitter bot file, which will then, using the Twitter API, respond on behalf of our bot with the new image. So again, pretty conventional for any sort of Twitter or chat response app, just with the caveat of we're passing the image off to this sort of like anomalous AI or machine learning function that we have. So let's take a look at the code. I have it listed here, and I have it listed again at the end of the presentation. But if we can take a look. So over here, this is the Twitter bot file. I'll go through this quickly to explain sort of what it does. Essentially, up here, we're using the Tweepy Twitter package to be able to sort of like, it's like an API wrapper for Twitter, handles your credentials, etc. And so there's really only two main things we're doing here. First, we're just going to define a class for our bot. It's going to have these things that I'm importing from credentials, which I have stored in another file. And it's going to instantiate itself down here. And when it has a positive event, it's going to, like if there is media, if there's an image in a given tweet, it's going to extract that URL. It's going to download it. And then I have some hard-coded paths over here. But essentially, it's going to call over here subprocess. This is where it's calling the machine learning model that I have to perform the style transfer. It's going to then return the output path of this file locally, and it's going to then respond to the given user. Hey, here's your painting with the username and the image. So pretty straightforward. And honestly, if you were to substitute this line here in subprocess with anything else, you could just return a static image. You could return like a Google search of the first image that you find with a given word. So again, nothing in this part here is sort of unique to AI or ML. I've abstracted that away into this sort of like calling this other script that I have. But even this isn't too complicated. So let's take a look at that. So this is just a bash script over here. Essentially, like I said before, think of this as a black box. Think of this as a function. We're running something in PyTorch or in Torch here. We're running a model in Torch, which isn't even the same language as our Twitter bot, which is okay. But all it really needs are a few things. It just needs the model that we have stored locally, which is over here, Starry Night. It's going to take an input image, which we've hard-coded in there to send to a certain directory. We give it an output directory that we want to throw the image to once it's done processing. And this flag down here is going to enable us to use GPUs to speed that up and make it really, really fast. Again, parallelizability and inference time is really important. And so for this exact same algorithm, if you run it on CPU, it takes, I think, about 5 to 10 minutes, depending on the size of the image. But with GPUs, this actually is almost instantaneous, takes seconds. But you don't have to take my word for that. You can actually see that if you tweet at the bot. So let's jump back over here. And so, yeah, if you pull up, let's see here. Oops. Hold on. One second. So let's take a look at some of these. With a request, here are some of the peers.
The screen sharing seems to have stopped, by the way.
Oh, hold on. Let me fix that.
Just hover over your video and then, yeah.
Yeah, the option to screen share disappeared.
Uh-oh.
Yeah, it's a little funky, but it's all good. I am pretty close to the end, and I have the link to the slides that I'll throw in the chat so that people can follow along while I'm continuing. I think that's probably the best way to keep going. So I just threw a link in the chat if you'd like to see these slides for the last few that I have before I finish my presentation. So I just have a few takeaways left. I can't show you, I guess, because I can't screen share right now for the responses, but within a minute, all of the responses are both ingested, processed, stylized, and returned, which is super, super powerful compared to the CPU alternative of making that last a very long time. And again, making that speed up from 10 minutes to instantaneous is really just as simple as throwing a GPU flag. And nowadays, with how easy it is to rent GPU instances from a lot of these cloud providers like Azure, Google Cloud Platform, AWS, it's a real alternative for a lot of people without needing to sort of understand how that works behind the scenes. So I guess I'll close with a few takeaways. First, although AI and machine learning are really difficult to understand conceptually, and I myself built a lot of sort of like analogies with black boxes here, I think it's really important to understand one step at a time as opposed to trying understanding everything at once, because that will definitely be overwhelming. And I think that if you can look at things at a more granular level, you can always think of them as individual functions, even in something very complicated like convolutional neural networks. These are all just sequences of like inputs and outputs. And so if you think about it in that context, you can always sort of parameterize things in a way that are more easily digestible. And if you're having trouble understanding a very large complex system, just try and break it down a little bit deeper and think of them as functions, because I think those are something that everyone really understands, whether that's in math or, basic things like, is this true or is this false, Boolean values. And then secondly, there are countless ways to incorporate AI and ML into your app, depending on your use case, skills, preferences, budget, etc. So don't feel like, oh, I don't understand, TensorFlow's tutorial looks really complicated to me. I may not want to get started with that. Or, oh, installing environments is very difficult. There's sort of like, as this ecosystem matures, there's solutions for everyone, depending on what you're looking for. I can say that pretty confidently as someone who sort of works in this every single day. So don't be discouraged. Really take a look, because I'm very confident that there is some sort of tool or way to get you to implement AI or ML in a way that sort of fits all of your seemingly unique constraints. So don't shy away from it. Sort of embrace it, embrace what your constraints are, and sort of seek help. I'm always available to help with that. I love being able to help people access the power of AI and ML in their apps. So if you ever have any questions about how you can incorporate that, feel free to ping me. I'd love to help people with that. And obviously, you can try this bot out yourself. It's live. It's on Twitter. You can tweet a picture at Starry Nightbot. Message doesn't really matter. And hopefully, as long as it's working and alive right now, it will respond near instantly with a stylized version of the picture that you tweet at it. So hope you enjoy that. And I have all of that code available on my GitHub here, linked at the bottom. All the slides from today's talk are also available here. I linked it in chat. Many of you are probably following along right now. And specifically, I did not build the model that works under the hood. I myself actually use that from some of the really awesome work at Stanford's AI and Computer Vision Lab. They do a lot of work on this all the time, and they made a really cool optimal algorithm for style transfer. And that's actually what my shell script is wrapping around. So again, don't reinvent the wheel. Leverage the resources that people are using every day around you, and build really cool stuff to solve your problems and achieve value, whatever that may mean for your particular business or just fun side projects.